Okay, so as you can see from the first slide, I'm not speaking in my own name, but on the name of the actual PI of SPICAV, Jean-Loup Berthaud, who could not make it to the Venus conference since he's in a PhD committee in the United States for the whole week. And so he gave me the slides, so to keep the experience as Berthaud-ish as possible, I've left the slides mostly untouched. So sometimes you will recognize the mark and the grief and the specificity of the Jean-Loup we all know and appreciate. Okay, so SPICAV is actually not one single instrument, but rather a suite of spectrometer that flew on board Venus Express. So you've got mainly the SWAR instruments. We won't give details about, since Anne-Carine is due to, I don't see Anne-Carine here, but is due to give a full talk about SWAR, specification, results, and archiving. And so I'll focus on the other two channels, namely SPICAV UV and SPICAV infrared, which, as you have guessed, deal with, respectively, the infrared range of the spectrum. So a short infrarange from 0.65 to 1.7, IOTF spectrometer with a sensitivity to polarization. Loïc Rossi has worked on this polarization specification quite a lot with us. The dispersing element for the wavelengths was an AOTF, so it's an acoustic tunable filter provided by IKI. So the RH channel has a very strong Russian community working on it from an instrumental and scientific point of view. In the UV channel, it's a grating the dispersing element, and with a slit to select and to improve the spectral accuracy. So both entrants are on the same side for these two channels, and SWA, which was proceeding mainly with occultations, as its entrants not in the same axis. So we are really, if you want to subdivide SPICAV, you've got SWA and then the two channels of SPICAV. And flawless operation of these channels through the whole mission. So both three channels of SPICAV did work till the very end, till late. I think the latest data we have probably from September and October 2014, and the mission ended not so long after that. Okay, so the UV channel first. The spectral range, so it's for the medium UV till almost the blue end of the UV spectrum, not exactly, but to the near UV. The slit is here, so it's just an open on the instruments, an open cut on the instruments. The slit was quite particular in that it had two different widths. One part of the slit was quite wide, so that we could gather enough signal on not so bright objects, namely for the star and the star occultation, since you do not need a slit to image a star and have a proper wavelength assignment and wavelength resolution then. And the narrow part when looking directly at Venus, which is very bright, so that here the signal is less an issue, but the spectral resolution and assignment was more of a concern. So so both parts of the slit could be used for different science objectives. And then the intensifier detector should be somewhere. Well, look for the cables here, but it has CCD, and there was an intensifier of light that will be detailed in another slide when we'll discuss the spectral response of the instruments. Okay, so the various modes of observation of SPICAV could be used pretty much in any mode that was used in during the Venus Express mission. First, the nadir one, when you aim directly at the surface of Venus, you could map the composition of particles above cloud deck on the day side using not only the particles, also the gaseous phase. You could map minor species such as H2O, which has absorption band in the infrared. Using the polarization information on the day side in the infrared, you could also retrieve the properties of the particles of the haze and the upper clouds. It has been detailed, I think, yesterday by Loïc Rossi here. In occultation, so you can use the occultation geometry and the peculiarities and the high sensitivity to the vertical resolution to have vertical profiles of minor constituents, isotope in the case of water vapor for H2O and HDO, and also atmospheric structure, the thermal structure above the clouds using hydrostatic equilibrium and CO2 as a proxy for temperature. And also probing the top of the cloud deck, and the extinction due to aerosol is clearly visible, and using especially solar occultation when the source is very powerful, you could get almost to the cloud top and a little bit below. You could also use limb observation, so without an external source of light, but just looking at the limb of Venus, mainly to study the emissions, the aneronomic emissions in the UV for nitric oxide. I think Jean-Yves Chauffret is here and can tell you more about it if you want to. Or HHFA, yes? No, I thought somebody wanted to interrupt me. And in the near-infrared, the O2 emission that was already shown in the Virtus presentation from Giuseppe and Pierre just before. And also replacing the sun by just stars. That's especially useful in the UV, where the sun is not as bright star as other star can be. And so in the UV and in the near-infrared, it can complement nicely the solar occultation, give it access not only in the terminator, but also on the whole night side hemisphere to vertical profiling of the same observable, so minor species, and also atmospheric density using CO2 and hydrostatic equilibrium to derive the temperature, and also the haze extinction and the aerosol structure. I think that in the UV for this, it's Denis Beliaev from IKI was in charge of this. Okay, so the number of targets, it's in a log scale. I want people to be reassured of this. So it mainly observed Venus, but not only. So of course, the source of occultation were observed of the sun and the stars. There are a few observations that are more surprising. I think most of Earth observation was done during the cruise phase or maybe at the beginning of the mission. Jupiter and Mars were observed too. That was a surprise for me when I saw this chart sent by Jean-Loup not so long ago. So I just give you the raw thing here. There are quite a lot of cometary observations. So to expand the science usefulness of SPICAV beyond pure Venusian science, there have been observations of other celestial bodies. And also here are not so many other targets than special modes of observation to look for specific cartography of nitric oxide or sulfur dioxide too. And even some galactic observations, I guess. I don't know exactly what he means by that, but anyway. Okay, so the principle of solar occultation, if you're not familiar with this kind of science, which may be the case since we are a lot of people here in the room. So you observe a star out of the atmosphere, so you get a spectrum of the star outside of the atmosphere, and then using the orbital movement of Venus Express, the optical path between the star and Venus Express goes through more and more atmosphere, and so you've got a growing extinction, for example here, of the spectrum of the star, and by having just a ratio of these two spectra, you've got a transmission. As Jean-Loup likes to say, it's a self-calibrated method. So doing the ratio removes lots of uncertainty of the calibration of the instruments, and these transmissions are actually a good observable to start with and to do science after. So we're removing the need to convert the ADU into physical unit first, for example. And so we had 5 bands on the detector to monitor the star occultation. So these 5 bands are just geometrical bands. The star was in the middle one, so the second, if you knew, 0, 1, 2, 3, 4 there. So the star signal is here and is quite clean here because the star is quite bright, and outside of the star you can't see anything. So you see the spectrum. This dimension is the spectral one, and this one is temporal, so following the occultation. So here, doing a cross-cut, you've got the spectrum, the unaltered spectrum of the stars you're looking at. And here you see the interesting part of the spectrum appears here, where wavelengths are progressively extinguished, not usually the shortest one before the longest one, and analyzing this gives a lot of information. But you also got signal on the other bands, and that might, so here the observation is quite clean. Mainly you just see ghosts of the star, just maybe scattering between the bands. But if you look at other places, you have other signal that actually can be extracted. So you know what we say, the noise of one observation may be the signal of another. And so here the noise for the solar occultation, that is actually the emission of nitric oxide at the limb, can be used to do aeronomy science afterwards. So actually there's always some science to extract from this kind of observations. So data processing, so getting a little more into detail. So the imaging spectra has the 5 spectra on the 5 band in this UV range, each second in occultation. For an occultation lasts for maybe 20 minutes to half an hour. So the level 0 file is just uncalibrated spectra in binary format and geometry in an ASCII text file. So the catalog does exist and is available normally. So from to level 1A is just to cleaning LU, so removing bad pixels I suppose. The flag matrix, okay, so yeah, that's for level 1A. You got the flag matrix to detect and to flag the missing data, or cosmic ray, or saturated pixels, so to remove the improper data, and also embedding the geometry, so in the FITS format. Then from level 1A to 1B, it's calibration from the ADU into physical unit, so whether radiance or a spectrum. Then quite a lot of treatment can arrive here when you want to remove, so the non-uniformity transformation here, physical units. No separation of contamination, we just have to have physical observables and then science occurs afterwards, so we don't anticipate on the science that can be made with this observation. And it's a little bit the same strategy as Pierre told for Vetis, for example, with the others. And the thread contamination, which has been, because it's over now, quite a big issue with SPICAV spectra, but we know it better and better, and we have better and better way to take it into account, and I'll show it rather in more detail later. So then, going to science observables, so first the transmissions that can be accessed by ratio for the star occultation, it's quite easy. Okay, the radiance on albedo. Albedo is more tricky because it requires dividing by a standard. When you look at nadir data, to have an albedo, you divide your spectra by a reference solar spectra, and the way you choose exactly your reference spectrally, and the way the nadir spectra are cleaned, especially when the ratio becomes more or less 0 over 0, so you become very sensitive to any departure in your processing. So here it's quite a little more tricky. And so for level 2B, then going from this, that's the actual, most of the science work that can be done from this, and then inverting the star occultation data into density profiles of CO2, ozone, which has been detected by SPICAV. It's actually one of the main highlights we have for SPICAV science with Venus Express, the detection of an ozone layer by Franck Montmessin, and also aerosol profile for the continuum. Temperature profile, so derived from the CO2 profile. The current density of SO2 from nadir data, you can't have access to the profile in nadir, but you can derive current densities which are observables. And also the vertical column of ozone aerosol can also be inferred from, I guess you wanted to say SPICAV and not SPICAM. The confusion is quite understandable because SPICAM and SPICAV are really twin instruments, and so the methods that have been developed for SPICAM can be more often than not applied to SPICAV data too. Okay, so that's an example of a raw image of the CCD in a log scale here for the canteen ADU, so it's a log of ADU. And it shows actually the what I mentioned about this trelite. So most of the spectra, most of the photons from the stars, which is, by the way, Alpha Virginis, alpha is written weirdly, but anyway, which is named SPICA. So SPICAV and SPICA, of course, chose the acronym. So I think it's a little tongue-in-cheek choose from Jean-Loup. And then, so most of the photons appear aligned with line number. So doing a cross-section here of the CCD would give you access to the spectrum of the star. But you can see that a significant number of photons appear, well, first in the first halo around the main spectrum, but this halo extends actually quite far here. So you've got non-uniformity of the CCD that is visible here, but that's not a physical signal here. But you've got quite a big halo, and we divide this into the proper photons, the core photons, which is just what is expected from the instruments if it were perfect. So just a point spread function that is due to the optical build and the optical choices that have been made during the design of SPICAV. And the other one, which are a little more surprising, and that probably come from extra scattering processes somewhere in the instruments, and we have quite a good idea of where it happened. And so we have model hypothesis. Actually, the PSF can be separated in two contributions, the core PSF and the halo PSF, which are treated quite differently. And usually the halo photons are just not to be taken into account. Okay, so this is a slide half in French, half in English, but be reassured I will translate most of the French for you as I comment this slide. So if we had a core only, so photons go through the sapphire window. No, not in because for SPICAV we have no sapphire window, so it goes directly through the fluoride of magnesium window here. Then it goes through the intensifier, so photon give birth to electron. Electrons are then accelerated by applying a high voltage on here. So we've got about 10 to the 4 electrons for each photoelectrons that have been produced by the photons here. So photon become 1 electron, becomes 10 to the 4 electrons after intensification. Then you've got CCD fiber and the detector on the other way. So assuming that, not assuming, but knowing that the electron here can have a small spread, then you expect a small, a PSF with electrons or neighboring pixels here coming from 1 photon here. Okay, but once you take into account the scattering of light within the fluoride window in the electrons, that is quite thick, actually 4 millimeters, so it gives, even with a small angle, quite a large spectrum here, then you actually convolve this small PSF with a much larger one representative of the scattering, the non-scattering process within the magnesium fluoride window. And so that's the hypothesis we have on this light. It's due to scattering of light in the entrance window of magnesium fluoride here. And so taking that into account, we can, now that this PSF is well characterized, going from level 0 to level 1A, for example, you can see here that these photons are actually photons coming from elsewhere on the CCD that should not be here, but that come to the pixel you're reading. And so knowing that into account and with the proper PSF, you can go from these raw spectra of a star to a clean spectrum, so slightly more resolved also, and with a signal going sharply to 0 where it should go to 0. So we have several observations like this when we know that we should receive no signal at all, and that are very useful in characterizing the exact spread of light on the CCD. And so going on this, you can then have the absolute spectral flux on target. And so the next step of processing, of course, are much cleaner once you've done the job of going from 0 to 1A more properly. And that's a job that has been done first for a while, because we wouldn't have been able to do much science without getting there from there to there. But we're still on the process of perfecting these early steps of the processing. We've had some engineers working at Letmos on these issues, and so the whole archive will be reprocessed in a much cleaner way in the months to come. So it's not over yet. So the high-level product, you've got, I mentioned this, the transmission. So you can, once nitric oxide aerodynamic emission abstracted, you can use cleanly your stellar occultation data and giving transmissions that you can then invert into CO2 or free. So that's an example. The figure comes from SPICAV actually, but these are actually the same physical processes, the more very similar instrument, and so the science and the algorithm to do science are very close to each other. Temperature profile is too, so okay. I already mentioned all that, so I come in next. Okay, so now you must read these slides with Jean-Loup Berthoud's voice in mind, because these are not my words. These are okay. So the PI mode, when you were talking, Jean-Loup, about archiving. First step, I think it's a little at the 5 stage of grief, a little bit like this. So first step for Jean-Loup is anger. Some people outside the team is going to steal my data. It's an understandable process. You invest a lot of work and energy for years and years into designing an instrument, so you might be quite possessive at first with the data coming from this instrument. So that was the first step. The second step is despair. Actually, nobody is interested in my data besides my own team, which work with me. The other people are not really demanding or asking for SPICAV data. So actually, wow. So the first concern disappears and leads to the sadness and the stage of the grief. Then you've got the shocking truth. I left it this way because it's really. Then Jean-Loup realizes he's going to die someday. And so what will people be able to do with SPICAV if he's being too retentive of information, or the SPICAV expertise can be lost once the expertise is lost? That's the Jean-Loup way of phrasing it, but we all know that people just enter lab, leave labs, go to retirement. It's less severe than death. And so, with all this process, the expertise can be lost. So what can we do so that all the work that we've done before is not lost? And so he's thinking ahead. So that's the acceptance stage now. So a legacy for future generation, public archiving is a necessity, and effort must be put in it. So put clean data, calibrated as a legacy, and for comparison with other missions, especially Akatsuki, which is now the near future of space exploration of Venus, and very promising things we all saw this morning. So that's what Jean-Loup went through in his mind when with archiving, which may explain why the archiving efforts begin maybe a little later than for the instruments, but we're catching up very fast. The take-home message is that it's taking very seriously. People are working full-time in Latmos to produce this and to deliver this to ESA in time. So, okay, you're happy with this? Ah, there's a step 5, excuse me. Even now, yeah, and that's important to put nice data open to the whole community, because people outside the team may see in the data things that we have not seen for a while. That's why we put everything public. That's the endeavor of science to do this all together. And so we have to make this possible. And so we have to make it public with all respect, so that scientists all over the world can use the data and make live the legacy of the SPICAV work here. Okay. So the plan for PSA archiving. So most of level 0A and 0A in UV and 0B in IA have been provided to PSA. The level 1A in UV is available for the release free. I think the extension and release follow more or less the same terminology and calendar as Pierre and Giuseppe told before. So it's very extension of Venus Express mission beyond the nominal mission. In the near future, so not so long in the future, a tool will be also delivered so that we produce automatically level 2A calibrated from 1B. So the strelite will be removed and will be removed cleanly. For those of you, I'll enter just a little more into a little more technical detail, but for those of you interested in the UV spectra, it means that the whole range between 170, 80 nanometer and 2 nanometer that was not properly usable before of this strelite, because strelite become an issue when the sun especially becomes not that bright. So these shorter wavelengths will become much more clean and much more usable. That will give access to a CO2 absorption band, especially in Nadir, with which a lot of science, I guess, can be done with it. So new science can open as the data are clean better and better. That's important to tell. It's not just technical thing. It's also, it has science impact. And by middle 2017, we'll have probably the whole pipeline operational, and so all things will be available in the PSA at ESA. Now, the outstanding Venus question, it was also asked to all PIs to so establish, yes, the evolution of UV albedo on Venus for long term, and the calibration stability is quite an issue. Well, the young Jolly who is here has known this for the VMC study too. And when we see variation in the UV, we always have in mind the fact that is it due to the object I'm looking at, or is it due to the edging of the detector? So normally we look at stars to be sure that we see the same thing. We can look at differential brightening or darkening of what we see, because if it's a difference with location, it's probably not due to the edging of the instruments, but we have to make these things very sure. So once the calibration stability is assessed, the long-term trend will become more and more known with precision, and that can give insight in the medium to long-term evolution of Venus on a yearly time scale. And we know that things happen on a yearly time scale on Venus, so that's not just theoretical, but it's a true science need here. The correlation with VMC, with VMC making progress, I suppose also with the calibration, the cross-calibration between VMC and SPICAV is important, especially to correct UV markings and the albedo together. So we've got both the geometry and radiometry to have agree here, especially now that in the later part of the mission, a new zigzagging mode has been implemented for SPICAV, namely wobbling Venus Express, so that the field of view does not only do latitudinal scan, but also sweeps in longitude, so that you've got some of partial maps in latitude and longitude with SPICAV, because SPICAV is not normally a mapping instrument, but moving the spacecraft, you could have partial maps and sometimes maps. And these maps so are especially comparable with VMC data, which are pictures and maps, therefore. Analysis of the scattering phase function, so not only in polarization, but also in photometry is of special relevance. So polarimetry has been used and has yielded good results. If we can use also the photometry that comes naturally with it in the UV and in the infrared, that's also a nice product to use with it. using the aeronomy emission as tracer for the circulation in the upper atmosphere is also of special interest. Looking for correlation, there's an animation afterwards showing this, with the caveat that NO emission is also moving with time, so it's not exactly a passive tracer to do the circulation with it, but it's, well, much better than nothing anyway. And a slow variation, I think long-term variation of cloud top altitude using a full database of star occultation. Actually putting it together with all wavelengths, we can investigate the temporal evolution also of the extinction profiles, especially so to detect variation of cloud top altitude. And also in nadir geometry using CO2 band and make sure both agree with each other. Okay, so that's something of quite relevance to, for example, Bob Carlson's analysis. But this is a spectrum, a UV spectrum of SPICAV in a location where not a lot of SO2 is present. Actually, the blue curve is the best fit without any SO2, and the black curve is the best fit assuming SO2 is present. And so the difference here is less than the noise, which means that we have just an upper limit and not a true detection of SO2 for this spectrum of SPICAV. It's not the case for other places where plenty of SO2 has been observed. But so here you've got the decrease here is therefore not due to SO2, but due to the first beginning, the short end range of the UV absorber. So that's actually the very beginning and the constraints we have on the shorter end of the wavelengths to constrain and to characterize the UV absorber. With vertice visible, you can have the other branch normally. I saw just a superimposition of plots of the albedo derived by vertice and SPICAV can give you this kind of shape, and putting both together can bring lots of constraints on the possible candidates to have exactly this shape, the spectral shape of absorption from the UV. So that's cross-instrumental science that becomes more and more easy to do, and that will have to be done to extract the full sense potential of Venus Express. So that's an example of what we can do in the future, and well, people are all working on it, but that's something to keep in mind. Also, this weird variation, that's Ariana Picciali's work while she was a postdoc in LATMOS. So looking at the CO2 level of, let's say, constant opacity level, with time, you see sometimes strange and continuous rays of the cloud top, not the cloud top, rays of the gaseous atmosphere, since it's a CO2 level here. For a few consecutive orbits, you can see a trend with the atmosphere moving up and moving down. So what can explain this? The current hot topic to explain this is geographical relationship with possible topography. There will be another abstract by Jean-Louis Berthaud, so myself will present Jean-Louis Berthaud's work tomorrow, about all the possible correlation between topography and other atmospheric observables. And it becomes more and more solid and integrating. So one of the take-home message, I anticipate a little bit to the end of the talk, is we have to map everything we know with respect to longitude so that we can investigate exactly the effect of topography on the atmosphere. It was neglected for a too long time in the mission, but now it becomes the very thing to do right now altogether, doing science with SPICAV, but also other instruments. So that's an NO map, I guess, with a few. So Nicolas Chaperon here, working an engineer here, and Jean-Louis Berthaud produced this map. So you get the field of view of SPICAV using a sweeping mode. So you see that I said that by putting a wobbling with the latitude scan, we can have access to the second spatial dimension, and so turn SPICAV into an imaging spectrometer and not just a spectrometer. And so it's much more limited than what Vertice map can produce, of course, but it's a nice complement to this. So I suppose Jean-Claude, you have lots of things to say about this. Solar scans too, we have not observed. Okay, we're out of time. Okay. Well, I will speed up a little bit. Jean-Lou's way. Okay, I can do this. So we not only observe Venus, but also the sun. So it's an image of the sun here. It's been a work mainly done by Eric Kemmerer at LATMOS, for example. So a few maps every MTP. Even one during the transit on Venus for comparison with, I think, the ISS, also an instrument to observe Venus transit at that very same time. It's important because with SPICAV and the sun, we can produce new reference spectrum for the sun that could be used for other people. So the highlights, these are the main science highlights. I won't detail them in detail, because if you're interested in one of these highlights, please contact the person of the light column. That's how the slides should be read. So if you see a topic of interest here, you contact the person there. And so, well, I won't address this more in detail. That's a second slide from Jean-Loup. It's really a Jean-Loup slide. And then, conclusion. We are not numerous enough at Latmos to extract the whole science from SPICAV data in a reasonable amount of time. So we need you to look into SPICAV data and do science with us here at Latmos. And we're very demanding on this. That's one of the main take-home message. The archiving is in progress. The first data are already available. We'll reprocess and give this in the month to come. Now it's a matter of month, and the calendar is well defined with ESA, so it's not ambiguity on this. All this temporal variation need real cross-correlation with other instruments, whether VMC, but also other UV cameras, for example, on board Akatsuki, or any UV data we can have, HST2. I don't know if Candice is here and can address this, but the more UV long-term data set we have, the better is it to characterize the aging on the instrument. So we're demanding on the temporal dimension very much. And, well, distray lights and vertical profile work. I think I addressed everything, and it's over now. Thank you.